All right, so last time we talked about this tool called isInstance with a lowercase I. And that's a Boolean expression, or a Boolean operator, if you will. I guess if we're being technical about it, it is a function that returns a Boolean value. The way it's used is as a function. You call isInstance, you pass it two values, the value you're comparing and the value and the type of class you're comparing it to, and it returns a value of true or false as to whether or not he is a member of that class. Okay, and that allowed us last time. Remember, we created quarters, nickels, dimes, blah blah blah. We were, just kind of randomly generated these objects, and the objects were all almost identical to each other, but technically they were different kinds of objects. And then we were able to go through and see who was who in there. So, we created these quarter, dime, nickel, penny, and the only difference between these guys is the fact that they have a value that's different. Okay. Now we could. Today, what we'll do is we'll take this one step further and look at the inheritance model, but just reviewing what we did last time is we had these four classes, then we went and we created a list. And a list in Python is different than an array in Java. So when we originally first talked about lists, and I mentioned this idea of an array, collections of things. And this kind of goes down to the difference between strongly typed and loosely typed languages. In a strongly typed language like Java or C or C++, when you create an array, you are creating a collection of like things. So everything you put in that array must be identical in type. Now, having said that, let me just spell this out a little bit because it's a pretty important concept and it's a little abstract. I'm just going to call them Java arrays for right now, but you could replace Java with C, C++, C#, pretty much any strongly typed language. So Java arrays, we'll say like lists, and I think we have a slide similar to this much earlier, but like lists in Python, but all stored values must be of the same type. All right, something like that. Where in this case, with Python, we just haphazardly created a list and said, here's a list, it currently has nothing in it. Now, because Python is loosely typed, we could just throw whatever we want into that collection. We could throw integers in there, we can throw quarters and pennies and nickels and cats and dogs and strings, it doesn't matter. We could throw all sorts of stuff in there. Now, you might start arguing that the list uses some of its utility if you have very dissimilar things in there, right? And this kind of goes to like how we organize stuff at home. I mentioned that computer programming helps us solve problems in a similar way to how we solve them at home. So every programming language gives us facilities for mimicking a lot of those things, right? So if you go out to Target or something, you buy a big, storage container, one of those that you slide under the bed, and you label it, I don't know, taxes or something like that, and you only put taxes in there, at this, your previous year's taxes, now you have a collection of like types. So if you need to go back and review your taxes from 6 years ago, they're in that box, right? Okay. Now, if you just put a piece of tape on there with a big question mark on it, and you basically just fill the box with stuff until it's full, and then you lose something, everybody, it's kind of like the junk drawer that most houses have. We have a junk drawer somewhere, and you look for whatever you're looking for in like the common places. Then the last ditch effort is junk drawer, right? Something like that. It's not an organized model. You're basically taking a shot in the dark. Okay. Now that doesn't say that in real life a junk drawer doesn't have a purpose. Sometimes we just have little pieces of junk that we're like, well, I don't want to throw it away, or you don't want to throw it away today, something like that, and it just collects in there and you find it 40 years later or something like that. But in that particular case, it is of like type in that it is junk. All right, but you really can't go and, that remind me later, you really can't go and just find it find stuff in there quickly. So we might say from a utility perspective, Java with its arrays, which we can, I've been referring to our list in here as collection types. Its arrays allow us to, or kind of force us into picking a type. We have to label the basket taxes. Now, that's only mostly true, and we'll be able to explain the rest of it because you did read the section on inheritance today. So I'll talk about that here in a second. All right. Whereas Python, because we don't have types, we probably should throw like types into a list. That's probably the utility we're looking for from a list collection, right? We want to store a bunch of numbers, or we want to store a bunch of coins, or whatever it is. That's probably what we want. But you don't technically have to. You can put whatever you want in there, okay? Now, let's say I wanted to store a bunch of numbers. In Java, I would say something like int array AR is equal to new int array 100. And that's going to give me an array capable of holding 100 numbers. Okay, so I went to Target, bought a Tupperware container big enough to hold 100 numbers, whatever that means. Okay, where the same thing in Python would just be AR is equal to, put a little space in here so you can tell it's the little list thing. AR is equal to the empty list. So in Python, we don't put a limit on size. So in Python, these guys are actually implemented as something called linked lists. And we actually talk about those in CSC200 in our data structures course. We write our own linked lists, which are dynamically sizable lists at the additional cost of performance. Right? So they're slower, but they're malleable. It's like the big Santa Claus bag. You get the little Tupperware container to hold your taxes for this year, and every single year you just put more and more taxes in there and it never runs out of space. That's how lists work. All right, so this is the Python version of that guy. Now in Python, I can throw numbers in here, or in Java, I can throw numbers in here. In Python, I can throw cats and dogs in there. Java would not let me do that. Now, I technically can cheat a little bit. We talked about, and let's talk about object-oriented languages. So the way object-oriented languages are built is we have this top-level dude here called an object. And he's built into the language. It's always object like this, or maybe it's a lowercase o. There's some language where it's just obj. Python is probably an uppercase O, but we'll screw with it until it comes out right. But there is this built-in type into the language known as object that represents the most basic form of something that is real. Basic form of an object. So last time when we created quarters, a quarter was an object. We didn't have to specify that. It's automatic in the model. We defined a class. Classes are of type object. The default, if we don't say something otherwise, is it's an object. So quarter, dime, nickel, penny. All right. So those guys are all, they all inherit from object. That means they get all of the commonalities that object provides. And then they further differentiated themselves by quarter having a value of 25, dime having a value of, and objects don't have values. There isn't like I called it value, didn't I? Yeah, value. So objects didn't come with a value variable. That's how we further differentiated our objects from our coins from an object by saying, oh, these guys also know about a value. And the value for a quarter is 25 versus a nickel, blah, blah, blah. Okay? Now, at this point, these guys are all objects. And we have this relationship called an is-a relationship. So we could say that a quarter is a object. A dime is a object. A nickel is a object. A penny is an object. Is a quarter, is it true that a quarter is a dime? No. So that is a relationship doesn't go that way. Okay, so all of these guys, these four guys here, these are all objects. They all is a objects or are a object, whatever, something like that. All right. Now, if we were kind of interjecting the inheritance model into this a little bit, we might say that what do all of these guys have in common with each other? We might say that they're all coins, right? So we can drop this down here, and I'm going to create a coin object. All right. Now, what kinds of coins exist? Lots of types of coins exist. Yeah, so we have the example of what we commonly, I say we commonly use, but when was the last time you actually had to use one of these? It's not as common as it used to be, right? Now you use your points in your card, you use a credit card or something like that, and God forbid you have to find a quarter. So that's where we have the junk drawer in your car, right? Where you just have like something that you just have stuff in, and you figure, I think I have coins down there somewhere. And then you're just reaching in and you start running into sharp objects, and you're throwing screwdrivers down there and all sorts of stuff. All right. So, but coins, we might say a coin has lots of things associated with it, right? So a coin probably does have a value, correct? But a coin maybe has a country of origin, something like that, and then a mint date, mint year. Just leave it like that for now. We could probably come up with more stuff, but we're starting to get an idea of like, oh, okay, well, I'm creating an object class for representing coins of all types, right? So these are coins of all types. Now, every coin has a value. Every coin has a country of origin. Every coin has a mint year. All right. Now, we could say the next level here is quarters, dimes, nickels, and pennies, or we can maybe say this is a US coin. All right. And with US coin, we might go ahead and say country of origin is always USA. Okay. Now, as various coins come off the press, they're going to have a mint year, and then if it's a quarter, its value will always be 25. If it's a dime, it'll always be 10, so on and so forth. But because all of these is a quarter is a US coin, which is a coin, which is an object. Makes sense? How we have this like hierarchical chain. That allows us to ask various questions. All right, so we're going to kind of create this model here. So go back to the, I think it's just parentheses at the end of the thing, right? Yeah. All right, so just looking at the stuff here. So we're going to have a coin. Then they created a produce. Well, coin is to item for us, right? So our coin is their item. And then they're creating some produce. That's going to be like a quarter for us. And they're saying this guy is built in terms of item. And we'll write this in a second. Then we build our constructor. But notice the very first thing we do here is we actually call the parents constructor. Then we further separate ourselves. All right, so if I come in here to our code, I'm going to go ahead and I'm going to define, we're going to say class coin. And we're going to def underscore underscore init underscore underscore This guy takes self in. My pit crew's here. This is my wife Tabitha, by the way. I think there's a plug there.
Okay.
And then the other thing goes down in this little circle thing. It might be that I was too fat for it.
That's what I'm wondering.
I was like overheating the battery. All right.
How can you tell if
It's got a red light on there.
Okay.
All right, thanks.
Good? You're welcome.
She's a COBOL programmer, so she's done this stuff for a long time, but with a really, really, really old language. All right, I'll see you later. All right, so now you know she exists. You know, a lot of students who've been here for 4 years have never met her. She doesn't come to a lot of the events and stuff like that. She usually has church things those nights, and so rare few. All right, so we have our constructor here for init. Now, there is kind of a magical line. I think I mentioned this to you last time, but in case I didn't, there's going to be an object dot underscore underscore init underscore underscore self that's getting called. Okay, so when we create our constructor and we don't specifically call our parents init, so like when we created quarter, we did not create quarter with a certain object in mind. We just relied on the fact that, okay, Python's going to magically make this thing be an immediate child of generic object. Okay, so there's a kind of a little invisible thing here, object, like that. And I'm not positive whether it's object with a capital O or a lowercase o. We'll probably find out when we run it, but you know, in any case, the logic here still follows. You know, I have a quarter, which is an object, but I didn't have to say that. Okay? But before this line in here, there is also a line that's interjected there that looks like this guy. It calls the parent's constructor. Make me an object first, then I will differentiate myself from it. Okay? Because the object constructor might do some magic for like getting memory addresses and, you know, whatever it means to be an object in that particular language on that particular operating system. So we're really relying, I mean, I don't want to undersell what's happening up here at this object level. This guy right here, there might be quite a bit of magic happening up there, depending on the language and depending on the model and stuff like that. We don't have to worry about it. But any object we define is built on top of that, built in terms of that. That makes some sense? All right, so any way you cut it, when we create an object, that dude's constructor will get called, whether we do it directly, or in the case where we're directly inheriting from object, it happens for us. And it says, look, I'm going to do that initial setup of creating an object because you don't get to be an object until we call his constructor, and then you can differentiate yourself. So Python kind of shows its age in that it's actually kind of interesting with Python from a language creation perspective. Python shows that it's a relatively young object-oriented language from the perspective that it does this call for us. We didn't have to write that. It's a little bit of a wonky looking call, but now we've kind of gotten used to the whole underscore methods. So we kind of get that, oh, that's just what those methods are called. It's something built in. But it's still kind of a wonky method. In a lot of other languages, it might just look like self, like that. That's how you would call the parent. But because of the Python being an interpreted language, we kind of have to pass around that variable self, and it just works a little differently. But it's just syntax difference. It's, at the end of the day, the concepts are the same. Okay, so in any case, if we don't put anything in here for coin, it will automatically call the parent's constructor. Okay, so it'll build itself as a generic object and then further separate itself. And what did we say that a coin will further separate itself as? We said a coin will have a value, it'll have a country of origin, and it'll have a mint year. So what we're going to go ahead and do is we're going to say that it's not going to make a whole lot of sense for us to have a generic coin. We're really treating a generic coin as a building block of bigger things. so we can give some structure. So usually this would be called something called an abstract class. In the 3 sections I gave you, did it talk about an abstract class yet? It's not overly important. Just the overriding concept is, here, I'll just put it in the notes real quick. Heavily. Well, you mean inheriting from other classes? Oh, absolutely. I mean, like we've seen like the string method. That's super common. If you want to make objects and all of a sudden every time you print an object, it gives you crazy memory address, all day long you're overriding the string method. Good.
Overriding the functions of the base class. The derived class.
So, well, that's the case even with object. So object has if we're going to say object is the base class, object has a method called underscore underscore str underscore underscore. And we can either take it as it is, or we can override it and give ourselves some real meaning to it, which would be pretty common. Whereas in our picture here, so to coin, the base class is object. To US coin, the base class is coin, who has a base class of object. To quarter, the base class is US coin, who has a base class of coin, who has a base class of object. So you could actually override the string method 3 times in here. So you can decide that a coin has his own string method that is like, look, I am a generic coin, but if you're looking at me here, there is something wrong. Because you just dug something up in the sand that shouldn't exist. We don't have a thing in reality called just a coin, right? We usually can give some sort of historical placement or whatever to a coin, but it still is a coin. So we're kind of thinking about it from how do human beings solve problems again. That's something we said at the beginning of class today. If somebody dumped out, if you had a jar in front of you that was filled up with quarters, dimes, nickels, Canadian money, blah, 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 and somebody said, is this a jar of coins? You would say yes, right? Because from a human being perspective, we're looking at them and say, those are a bunch of coins. I don't know what kinds of coins those are, but those are coins, right? So in that particular case, it may make sense for us to create a coin class if we needed to problem solve at that level. If we needed to have a collection of coins, we have a jar of coins, and as we dump them out, we have to start identifying those coins. And we can identify those coins using our isInstance function that we introduced last time. We can say, is this an instance of a US coin? Or is it an instance of a Canadian coin? Or of a Russian coin? Or so on and so forth. Okay. They're all coins, but they could also be US coins. It could also specifically be a quarter. So a quarter is an instance of a quarter. It's also an instance of a US coin. It's also an instance of a coin. It's also an instance of an object. So isInstance would return true for all of those questions. So it allows us to granularly ask the question. If I hold up a banana, I say, is this a coin? You say, no, it's not a coin. Okay. Like, little did you know, in some African nation, these are coins. There's actually probably truth to that. There are probably some countries that, but I guess you probably wouldn't call it a coin at that point. You know, they just use fruits and vegetables and stuff as bartering system for, you know, meat and services and that kind of stuff. Probably would make life simpler. Is it? Which part of that was the funny part?
There's something.
There's some gold in there. By the time you're a senior, soundboard's gonna have like 19 pages. You're gonna have downloadable content, 99 cents for audio packs. Some students made a soundboard or something similar to that several years ago. It was going around, I think, Wittenberg. I think I've said, have I yelled like "shut up" in class in here before? Yeah, because that's like one of my go-to moves for years. And you haven't even heard it at full. I can get a whole gymnasium to shut down. I can project. I can project. So so apparently that was like making its rounds in the dorms. I got back to like President Ferry and stuff like that. He thought it was funny, but I'm just saying that it's like, oh yeah, my teacher just he yells at us and stuff like that. And then until people meet me, they think I'm just like this mean person, but I am a mean person. But so. All right. Oh, abstract classes. Okay, so when we say a class is abstract, now in Java, for example, we're going to recover this next semester in 250 with Java. Java has a specific keyword for abstract, and you're going to find that being pretty common between loosely typed interpreted languages and strongly typed compiled languages. That you're going to have a whole lot of extra words you have to throw in there in strongly typed language because you have to specifically say this is what I'm doing. But the concept of an abstract class holds throughout. So we're going to say an abstract class is a class whose purpose is to support the inheritance model rather than have specific instances of it created. There might be some grammatical issues there, but close enough. Okay, so the idea in our little model here with our coin exists to differentiate itself from an object, but not to actually ever create a blank coin. Our intention would be to create quarters, which are US coins, which are coins. So we're never going to actually create a generic coin. We're never going to actually create a generic US coin. We would create the specific quarters, dimes, nickels, pennies, which happen to be US coins, which happen to be coins. So an abstract class exists for the sole purpose of supporting that inheritance model that then allows us to do things, for instance, like using the isInstance function we introduced last time, where I can ask a quarter, are you a coin? If yes, are you a US coin? If yes, are you a quarter? We can go all the way down to that level, but we can get multiple true responses from that if we've used the inheritance model properly. Does that make sense? Now, I would say that you could go through, and this is kind of based on his question earlier, the question I thought he was asking earlier about inheritance. You could probably go through most of your career never actually using the inheritance model. If you never use the inheritance model, what would you end up doing more of? Or duplicating code. Yeah. So you would have to, if you had 5 different classes that all had a commonality and you chose not to create that common core, you would just have to duplicate that common logic in all those 5 classes. Now, is that good programming practice? No. We're going to say that's not good programming practice. But can it be functional code? Absolutely. I mean, heck, before we had object-oriented languages, people did that stuff all the time. With procedural languages, we didn't have the ability to represent objects. Forget about inheritance. We couldn't even we couldn't even throw everything inside the bag. We just had wires laying all over the place, and it was fine. It just made do. All right, so idea here is that the inheritance model is a very, very, very good tool that will make your life easier in some situations. When we get into 300, the data structures course, we'll build a linked list. Our initial linked list we build is a linked list of integers. And then you say, well, what if I want to hold strings? Well, now you have to change your whole implementation. Well, if you built a linked list of objects, now you can hold anything you want and just extract the types from it after that. Okay, so having a handle on the inheritance model makes a lot of sense. Now, for us, the inheritance model is not a hard thing to wrap our mind around as soon as we start, go back to considering that programming languages attempt to allow us to solve problems in the same way to how we solve problems in real life. Correct? Every one of us has a parent. Okay, we have a couple of them. All right, so, whether they're around or not, we have parents that we got genetic material from. Okay, so we have some commonality from them, and then we further differentiate ourselves from them, right? You might have a parent with brown eyes, you ended up with blue eyes. You further differentiated yourself. That kind of stuff. But we got core components from our parent. And at the very top level, we're all human, right? And human defines some core components. It defines, 5 fingers, 5 toes, certain organs that should be present, and every now and then you have a mutation or whatever. But generally speaking, every one of us in here is human. More than generally speaking, every one of us in here is human, with the exception of me, maybe. But so we all have those common traits. Okay, but then between us and the instance of human that is Mike and the generic human, I have my parents and my grandparents and my great-great-grandparents and all that stuff that was, passing traits down through the lineages. That's what inheritance is, right? That's what this model is doing. It's allowing us to interject that if it makes sense. Okay, so try to keep that in mind as you learn new concepts with programming stuff. Is a high percentage of the time, the language is providing you a facility for something you already understand. You just kind of get psyched out by thinking that, it's another programming thing. But it's really actually the programming language's best stab at mimicking something that you already are comfortable with in real life. All right, that's why our challenge still is beginning programmers, when you sit down and you know the problem you want to solve, and you feel like you understand the syntax when you see it, but getting those two to match up is still a challenge because you're having to train your brain to solve problems that you could trivially solve in real life as a normal human. Like, you want me to sort this pile of coins into quarters, nickels, dimes? No problem. I can do that as a person. Right? But now you want me to do it with Python? Drop the class, switch majors, whatever it is. It takes time to bridge that gap. Right? Even though once you've bridged it, you'll think, why was this ever hard? Make sense?
Yeah.
That's the whole put the reps in, it's a sport, blah, blah, blah. The pros make it look easy. That's how I broke my foot, is doing the windmill dunk. I told you I fell off a sidewalk, but it wasn't that. It was... All right, so that's the concept of an abstract class. We're not going to focus too much. I'm not going to test you over abstract class in here. We covered a lot more in Java, and really it's more of in Java, if you use the abstract keyword, the language actually polices you. If you say this class is abstract, so if I came up here and I defined the coin class as an abstract class, which I probably would in Java, and then I just decide to screw up and go and try to make an instance of coin, it won't let me. It'll scream at me and say, you cannot create an instance of an abstract class. Python, it's class is a class. Just move on with life. Okay, so it's more of a concept that some classes exist for the sole purpose of a supporting inheritance. Some we choose to directly use. The sole purpose of supporting inheritance classes we would call abstract classes. Okay, whatever. All right, so back in here, we have our coin class, and this guy directly inherits from object, so we just use the default inheritance thing. All right, and we've decided that coins, in our little picture here, have a value, a country of origin, and a mint year. So we're going to go ahead and we're going to establish those three things, but we're going to give them like default setup values. That's the purpose of a constructor or initializer, is to kind of, if this thing was just born and given no necessary inputs, what is he? Okay, something like that. So I'm going to start with that, and you'll see where I'm going with this. So I'm going to say self.value. We'll start off at -1, just giving it a placeholder value, something like that. Then we have country of origin. Self.origin is equal to maybe n/a. And then we have mint year, self.year. And maybe just do, I don't know, we'll probably store that as a string to get the, it's actually an interesting question. We wouldn't do it as a string. We'll just say year 0. That way we can compare these guys to each other for age, one coin being older or younger than another one. All right, so that might be what a coin looks like right there. And then what we might do is we might say, let's go ahead and def underscore underscore str underscore underscore. All right, so we're going to override that one because if we just created a blank coin and then printed it, what would it print? Crazy memory address looking thing. Now we might want to just give ourselves a little reminder here. So we might want to go and do something like return a generic coin. So if I have something that is a coin and we happen to try to print that, it's going to print out a generic coin. Give me a little visual reminder that, look, you might have thought you were dealing with quarters or pennies. You're not. Okay, this is a coin. Good luck. So something along those lines. Okay. So we'll just override string there just as a convenience for us. Now what we would do is we're going to create another class here. So we'll say class US coin. We'll def init. Very first thing I'm going to do is I'm going to go ahead and call my parents constructor. All right. Now, you're going to see what's kind of going on with this here in a second because I'm going to update this guy here in a second. Right now, I've given it these like hard-coded values. But what we're going to say is, you know what? I'm going to be able to create a coin with maybe a couple of different ways. So I can, if somebody just creates a blank coin, I'll go ahead and just make a guess at these values here and hope for the best. But similarly, I can have a second constructor in coin. One that maybe takes in those extra values in case I happen to have them. And in that case, I can say self.value is equal to value. Self.origin is equal to origin. Self.year is equal to year. All right, so that kind of stuff. All right, so now I have two separate constructors for coin. Realistically, we are never going to actually create a blank coin, so I probably could actually dump this constructor if I wanted to. But I'm going to leave it there for right now, just so we can kind of see this model flow through. Okay, I'll put a little extra thing. So how does Python know which constructor I'm calling? It knows by the number of parameters I passed it. I think last class that I mentioned that crazy word, polymorphism. Okay. Same method name with a different number and or type of parameters. So we have two methods here called init. One of them takes no real parameters. Self gets passed around as part of the object-oriented model. This one takes 3 parameters. So if I call this constructor for coin, passing it 3 parameters, Python will know to use this version of init as opposed to this version of init. Make some sense? All right, so but what I've done here is I basically said, look, if somebody calls a no argument constructor and they want to make a coin for some reason, I'll go ahead and I'll populate those core values with effectively default nothingness to make math work or something like that. Okay? So that's my coin. Now we're going to say a US coin is a coin. So we're going to say this guy inherits from coin. And the very first, and we're going to have the constructor for this guy. When we create a US coin, he's also going to have a value and origin. Actually, he won't have an origin. He'll have a value and a year, right? Value and a year. Why won't he have an origin? If I'm building a US coin, why wouldn't he have an origin? We know it's a US coin. His origin is US. Right? So we don't need to take that as a parameter. So we'll go ahead and we're going to call our parents constructor. So we'll say coin dot underscore underscore init underscore underscore. We're going to call the version takes 3 parameters. One of them is value. We don't really have a value. Another one is origin. Another one is year. Right? So we can actually make the argument we can have a whole bunch of these init methods that take less and less parameters. But for right now, I'll go ahead and I will call my no argument one. So that will set up, actually, we'll call the full one. We'll say value. We'll pass in USA for origin, and then whatever year was passed in for this guy. So we'll go ahead and call our parents constructor to do that initial setup. All right. And then we can differentiate ourselves from there if we want, but we don't have to because we already differentiated ourselves by passing in USA as the origin. But we don't have a year, we don't have a value that's meaningful at this point. They were passed in here, but who knows what value and year were passed in. We're just passing the buck. Okay? Similarly, we can go ahead and def __ str __, and we can return a US coin, something like that. Just kind of give us a generic placeholder for US coin. All right. Then we have a quarter, and a quarter is going to be a US coin. That makes sense? And the constructor for this guy is going to be to call US coin dot __ init __ passing itself. We pass it a value. For a quarter, the value is 25. We don't pass it at origin because its origin is going to be a US coin. And we pass it a year, whatever the year might be. So why don't we go ahead and have the constructor for our coin here take in a year. So when it gets minted, we mint it with a year. So all the coins that came out right this year, 2019, something like that. So we'll just pass that year on through. So when we build a quarter, we build it just with whatever year that quarter was. And then a quarter is built in terms of a US coin, passing it a value of 25, and then whatever year we passed in, because a quarter is always going to have a value of 25, right? And then it's going to build that US coin in terms of a coin, where it passes in the value, it passes in the origin, USA, which we didn't take as a parameter here, but we didn't need to, and then whatever year we passed in. And then the coin constructor will go ahead and set those three values. All right, so that's what a quarter is. Now I can go ahead and let's do the same thing. Steal basically that. We'll do this for dime. The difference for dime is we pass in a 10. We'll do this for nickel. Difference for nickel as we pass in a 5. Do this for a penny. Difference for penny as we pass in a 1.
Okay.
That makes sense?
Yeah.
Now, since we already know that all US coins will have a value and a mint date, we could actually write our string function here such that it knows how to deal with all US coins, rather than overwriting string for all 4 of these. So we can say we're going to return, we'll go ahead and return an F string. So we're going to say value self.value, and then maybe year self.year. So anything that is a US coin will be able to show its value and its year. All right, and then maybe before it we say US currency, something like that. US currency, value, then year. So as we create quarters and dimes and nickels and pennies, and we give these guys a year, we'll make a whole bunch with just 2019 in them right now. All right, so here's me filling up my coins. I'm appending a quarter, but now a quarter takes in a year. So the year I'll pass it is 19 or 2019. 2019, 2019, 2019, like that. And then what we'll do is I'll just spin through all those guys and print them out. So I'll say for coin in coins, print coin. Something like that. So this will build up a whole bunch of quarters from 2019. I'm printing a bunch of stuff, and I'm creating instances of a bunch of stuff. And then when I go to print them, it should print out U.S. currency, whatever the value was, and whatever the year was. It's possibly interjected an error or something in here, but let's just see what we got. No, it worked. All right, so value 10, year 2019, so on and so forth, all U.S. currencies. That makes sense? Okay, so for homework for Monday, I'm going to put this code up on Slack. I'm also going to give you a little more reading assignment just to go a little bit farther. Be prepared for a quiz over what we covered in class today on Monday. Okay? And let me just look real quick. You can start packing up. We're done, but let me just look. I only want to give you a reading assignment if it makes sense where I'm going next. I don't want to just give it to you just to give it to you. So you did 13, 1, 2, and 3? Oh, but I didn't give you 4, right?
No.
All right, let's just read 13.4. That covers a little bit of what we talked about today. That is a thing. So just one little section. Get basically a free homework assignment out of it. And then study for the a potential quiz on Monday. What's up? 13.4, that's it. Just that, on what we covered in class today. Yeah, today. So study today's class, and I'm going to put the code up on Slack. The whole inheritance thing. Okay? So what I might do is I might give you some code. I'm not positive this is what it would look like, but I might give you some code like we have, and I might ask you what's the output, making you follow that inheritance model, as opposed to write a lot of code during the test. Yeah, so it would be probably reading code at this point. Sound good? All right, I will see everybody on Monday.